Good day, sir. Today I will explain the function of my main menu for running different numerical root finding methods. It loops indefinitely until the user chooses to exit. So the first line will this. This function declares a new function named root finder tool, and this line clears the command window but not workspace variables. And this while true starts an infinite loop. The program will keep running until the user chooses to exit explicitly. And this part displays a user-friendly menu with numbered options for each root finding method. And this choice input, choose a method 0 to exit, is a prompt. It prompts the user to enter their choice stored in a variable choice. And this switch choice begins a switch case block to handle the selected method. And for all these cases, start from incremental search down to the graphical roots, calls the function, and this case 0 displays an exit message and breaks out of the while loop, ending the program. And this otherwise displays an error message if the user inputs anything that not listed in the menu. And the last one, the fprintf, is it pauses until a key is pressed, clears the screen, and loops back to show the main menu again. So now we will run our code so that I can see all their functions, just like this. So we will begin our root finding methods menu to number 1, the incremental search method. So we will input here in the choose a method 0 to exit, so we'll choose number 1, and here it is. Muna siya ang mugawas sa inipindot sa number 1, and then we will give an example. So x raised to the power of 3 minus x minus 2, and then enter. Our initial value is 0, step size is 0.5, and our maximum iterations is 20. So as you can see, naay graph nga ni gawas, and in iteration 4, as you can see, 5 of x sub I is negative 0.125000, and for the 1f of x sub I plus 1, we have 4, so their product is negative, so sign change detected. And a root lies between x equals 1.5 and 2.0. So the plot shows a smooth curve of f of x is 1, and a red marker between 1.5 and 2.0. X-axis line for reference is y equals 0. So that's all for the number 1 incremental search method. So we will proceed now to the number 2. So press any key to return to the menu. So I will press any key. So, ibalik siya sa main. So, now we will continue to explain for the bisection method. So, we'll input here number 2. And then, I will give an example. Before I give an example for the bisection method, I will explain how my code works. So, the purpose of my code is this function performs the bisection method to find an approximate root of a user-defined function in a given interval a, b, where f of a times f of b less than 0. So it accepts user input for the function and parameters, and iteratively applies the bisection method, displays results in a table, and plots the function with the root. So, this line asks the user to input the function as a string, for example, x raised to the power of 3 minus x minus 2. Then, this string is transformed to work correctly in MATLAB for vector operations. This line defines how accurate the solution must be and how far the search should go. So, this line check for valid interval. Bisection only works if there's a sign change between a and b, meaning a root must exist between them. So, bisection loop, this finds the midpoint between a and b and evaluates the function there. So, then it checks how close fxr is to 0. If it's small enough or if the interval is tiny, it stops. Stopping condition. This one. Otherwise, it updates the interval here. So this ensures we always narrow the interval that contains the root. So for the plot function and root, here, mani ang plot. Pag-plot niya. So, and then for display the iteration table, the iteration results are shown in a iotable GUI style table, making it easy to read the progress. So now I will provide an example for the bisection method. So, example, x raised to the power of 3 minus x minus 2. So our lower bound is 1, the upper bound is 2. Our tolerance is 1, e minus 5, and our max number of iterations is 20. So, ngani gyapon ang gawa same sa incremental na ay graph, then naasad siya yung table. So at each step, the interval a, b is halved and xr gets closer to the root. Eventually, it converges around. So, ang xr na to is 1.52138, which is the actual root of x raised to the power of 3 minus x minus 2 equals 0 to 5 decimal places. So, ito ang final output displays the table of iterations, plots the function and the approximate root, and prints the approximate root by 1.52138, and so on. So that's all for the bisection method. So we'll press again the key to go back to the main method menu. So reserve. So we will now proceed to the regular falsy or false position method. So I will explain my false position method on how it works. So the first one, the input user enters a function as a string. For example, x raised to the power of 3 minus x minus 2. This one, Monisea. Inputs interval a, b, tolerance, and max iterations. Then it checks that a and b, I mean f of a and f of b, have opposite signs. And then this one calculates c using the false position formula. So c equals b minus f of b times a minus b over f of a minus f of b. And then it updates either a or b based on the sign of f of c. And stopping criteria stops when error is less than tolerance or max iterations are reached. So our output displays a formatted table of iterations and then plots the function and root approximations. So for now, let's start our example for the false position method. So we will enter here the number 3 for the false position. Then x raised to the power of 3 minus x minus 2. And our interval starts at 1 and ends at 2. And our tolerance is 1 e minus 5. And then our maximum number of iterations, we'll put this into 10. So, as you can see, gawas na agya po yung graph na nigawas. And then, this blue curve shows the f of x equals x raised to the power of 3 minus x minus 2. And for the red dots on the x-axis are root approximations from each iteration. Here. Ang root nito is 1.521377. So that's all for the false position method. So now we will proceed to the Newton-Raphson method. So we will put here number 4. And then for the code, the purpose is to find a root of a function f of x by iteratively improving an initial guess using the derivative f of x. So user inputs the function f of x as a string here, and the derivative f of x is calculated symbolically, and the user inputs an initial guess, tolerance, and maximum number of iterations, and then iterate using the formula. For the important functions of the Newton-Raphson is the diff, open and close parentheses for symbolic differentiation, and subs, open and close parentheses, to evaluate symbolic expressions, and loop to update root estimates until convergence. And now I will provide an example for the Newton-Raphson method. For example, is x raised to the power of 3 minus x minus 2. And for our derivative, we have 3 x and raised to the power of 2 minus 1. And our initial guess is 1.5. Our tolerance is 1e minus 6. And our maximum number of iterations is 20. So as you can see here in our graph, Newton-Raphson uses the slope f derivative of x to jump closer to the root. And with f of x equals x raised to the power of 3 minus x minus 2, starting from 1.5, it converges quickly to approximately 1.521, so on. This root is the solution to x raised to the power of 3 minus x minus 2 equals 0. So that's all for the Newton-Raphson method. And now we will proceed to the second method. So put here number 5. So for now, I will explain the second method. For the input function, a string converted to a function handle, initial guesses x sub 0 to x sub 1, a tolerance and max iterations. So iteration uses the second formula. So nagyan po tayo formula for the second. And then the absolute difference between consecutive approximation. The absolute difference between consecutive approximations is less than the tolerance or max iterations reached. So our outputs, iterations table showing guesses, new root approx and errors, and plot of the function, root approximations red circles, and second lines green dash lines. So I will provide an example for the second method. So example, we have cosine of x minus x, and then our initial guess is 0.5, and our second initial guess is 1. Our tolerance is 1e minus 6, and our maximum number of iterations is 20. So this one, Malaysia. Our approximate root is 0.73909 or 0.73908513. So this blue curve will show f of x equals cosine x minus x. So these red dots will appear on the x-axis at each guess made by the second method, and then kaning green dash lines will connect previous guesses to show the second lines used for the next approximation. So that's all for the second method, root finding. And now we will proceed to the last method, which is the graphical method. So we will put here, press any key, and then number 6. So for now, I will explain about the graphical method. So the purpose of this is to find and visualize approximate roots of a nonlinear equation f of x equals 0 by plotting the function and identifying where it crosses the x-axis. So how it works, a user input this one function entered as a string. For example, x raised to the power of 3 minus x and minus 2. And we have x minimum and x maximum, the interval over which to plot the function. And for the preparation, converts operations to elements wise. This wise to support vector input and converts string to anonymous function. So for the plotting, generates 1000 points from x minimum and x max. 2x max evaluates f of x and plots the functions. Plots the x-axis, y equals 0 for reference. And for the root detection, checks for sign changes and adjacent y values indicates crossing the x-axis approximate root. If f of x sub 1 equals 0, it detects an exact root. Marks red dots for approximate root sign change and for the green dots for exact root. So for now, I will give an example for the graphical method. So paste it here. Then our minimum value of x is 0 and the maximum is 4. So as you can see, here is the graph of our graphical method for root finding. So the code evaluates and plots f of x equals x raised to the power of 3 minus 6x raised to the power of 2 plus 11x minus 6 over the interval 0 to 4. And it finds that the function crosses the x-axis at 3 locations. Here, 1, 2, and 3. It will display the exact root for 1, 2, and 3. Dapat color green pero red ang nigawas. Bakit ko sinabi yun? Okay, so 1, 2, 3, go. It will display something like this for the exact root at 1, 2, and 3. You will see red dots exactly at x 1, 2, and 3 indicating exact roots. So these polynomial factors to f of x equals x minus 1, x minus 2, and x minus 3. So that's all for the graphical method. So thank you very much for watching my explanation about the numerical methods for the MATLAB. Thank you.